Hey there, friend. If you're here to unwind and drift into sleep, you've found the right place. Dim your screen, lower the volume, breathe slowly, and welcome, especially if you're new here. Let's begin. In 1994, a psychologist named Jerome Busemeyer discovered something that should have been impossible. He was studying how people make decisions, and he found that human choices violated the fundamental laws of classical probability. Not just occasionally. Every single time. When he applied quantum mechanical equations to the data, the inexplicable suddenly made perfect sense. Your brain doesn't think like a computer processing ones and zeros. It thinks like a quantum system exploring multiple realities simultaneously. Tonight, we're diving into why your consciousness operates through fractal patterns and quantum probability, and, more importantly, how understanding this hidden architecture can transform the way you navigate reality itself. Before we unlock these cognitive secrets, hit that like button and subscribe, because what you're about to discover will fundamentally change how you understand your own mind. Chapter 1. The Classical Mind Illusion. Imagine you're sitting in a cognitive psychology lab, and a researcher presents you with a simple question. Linda is 31 years old, single, outspoken, and very bright. She majored in philosophy. As a student, she was deeply concerned with issues of discrimination and social justice, and also participated in anti-nuclear demonstrations. Which is more probable? Linda is a bank teller, or Linda is a bank teller and is active in the feminist movement. If you're like most people, you immediately felt that the second option seemed more likely. Linda just sounds like someone who would be involved in feminist activism, doesn't she? The description paints such a vivid picture that your mind naturally gravitates towards the more specific scenario. But here's the problem. You just violated one of the most fundamental laws of classical probability theory. The conjunction of two events can never be more probable than either event alone. It's mathematically impossible for Linda to be more likely a bank teller and a feminist than simply a bank teller, because the category of bank tellers includes all bank tellers, whether they're feminists or not. You've just committed what psychologists call the conjunction fallacy, and you're in good company. When Amos Tversky and Daniel Kahneman first documented this phenomenon in 1983, they found that over 85% of participants made the same logical error. For decades, cognitive scientists labeled this kind of thinking as irrational, a systematic flaw in human reasoning, evidence that our brains are buggy computers running outdated software. But what if they had it backwards? What if the error wasn't in human cognition, but in the framework being used to understand it? For most of the 20th century, cognitive science operated under a seductive metaphor. The brain is a computer. Consciousness is software. Thinking is information processing. This computational model seemed to explain so much. Neurons fire in patterns, transmitting signals through networks, processing inputs and generating outputs. Memory storage, attention as a spotlight, decision-making as algorithmic calculation. The metaphor was so powerful that it shaped entire fields of research, from artificial intelligence to neuroscience to educational theory. The assumption was simple and seemingly self-evident. If we could just map all the neural circuits, identify all the algorithms, catalog all the processing steps, we would understand how thinking works. The brain became a biological machine to be reverse-engineered, consciousness reduced to computation, and the mind transformed into a problem of sufficient complexity rather than fundamental mystery. This reductionist approach achieved remarkable things. We mapped neural pathways, identified neurotransmitter systems, and discovered how different brain regions specialized in particular functions. The visual cortex processes sight. Broca's area handles speech production. The hippocampus consolidates memories. Each discovery seemed to confirm the basic premise. Break the system down into its component parts. Understand how each part functions, and you'll understand the whole. Implicit in this approach was an even deeper assumption borrowed from classical physics. Reality operates according to deterministic laws. Objects have definite properties independent of observation. Causes produce effects through local interactions. Probability reflects our ignorance of underlying deterministic processes, not anything fundamental about nature itself. This classical worldview permeated cognitive science so thoroughly that alternatives seemed either mystical or scientifically unserious. But then, researchers started noticing something strange. Human thinking kept violating the rules that classical probability theory said it should follow. The Linda problem was just the beginning. In experiment after experiment, people's judgments and decisions exhibited patterns that made no sense within the classical computational framework. These weren't random errors or occasional glitches. They were systematic, predictable, and universal across cultures and populations. Consider what happens when you ask someone two questions in different orders. Researchers conducted studies on political attitudes, asking participants whether they thought Bill Clinton was honest and whether Al Gore was honest. When Clinton was asked about first, people gave certain ratings. But when the question order was reversed, the ratings changed significantly. The act of answering the first question altered how people responded to the second question in ways that classical probability cannot explain. According to classical logic, the probability of two independent events should be the same regardless of the order in which you consider them. If I flip a coin twice, the probability of getting heads on the first flip doesn't change based on whether I asked you about the second flip first. The events are independent. Their probabilities are fixed. But in human cognition, this independence breaks down. The questions become what physicists call incompatible measurements. Asking about Clinton first creates a different mental state than asking about Gore first, and this different mental state produces different probability distributions for subsequent judgments. The mind doesn't contain fixed, pre-existing beliefs waiting to be accessed like files on a hard drive. Instead, beliefs exist in a state of potential, crystallizing into definite form only when the question is asked, and the specific form they take depends on the context in which the measurement occurs. This is precisely analogous to quantum mechanics. In the quantum world, measuring a particle's position creates a different quantum state than measuring its momentum first, and these measurements are incompatible because performing one changes the system in ways that affect the other. Heisenberg's uncertainty principle isn't about our lack of precise instruments. It's about the fundamental nature of reality at the quantum level. Properties don't exist as definite values until they're measured, and the act of measurement participates in creating what's measured. For decades, physicists understood this about electrons and photons. What they didn't realize was that human cognition operates according to the same mathematical principles. The implications are staggering. Every time you think about something, every time you make a decision, every time you introspect on your own mental states, you're not passively observing pre-existing information. You're actively participating in the creation of mental reality through a process that resembles quantum measurement more than classical computation. Think about what happens when you try to examine your own thoughts carefully. You sit down to meditate or engage in therapy, or simply reflect on why you feel a certain way. The moment you turn your attention inward, something shifts. The thoughts you were having a moment ago seem to change under scrutiny. The emotion you were trying to understand transforms as you examine it. The memory you were recalling becomes different in the act of recall. Psychologists have documented this for years, calling it reactivity, or the observer effect in psychology. But they typically treated it as a methodological problem, something to control for or minimize. The assumption was that there must be some true objective mental state underneath, if only we could observe it without disturbing it. But what if there isn't? What if the disturbance is fundamental? Quantum mechanics tells us that at the subatomic level, there's no objective state prior to measurement. The electron doesn't have a definite position that we simply disturb when we look at it. The position comes into being through the act of measurement itself. Before measurement, the electron exists in a superposition of all possible positions simultaneously, described not by definite values, but by a wave function encoding probabilities. Could the same be true for mental states? When you're not actively thinking about your opinion on some political issue, does that opinion exist as a definite, determinate fact about your psychology? Or does it exist in a superposition of potential positions, only collapsing into a specific stance when someone asks you the question, when you're forced to vote, when the measurement occurs? The evidence increasingly suggests the latter. Your beliefs, preferences, and even your sense of self exist in quantum-like superposition states, probability clouds of potential rather than fixed classical facts. This explains why you can feel genuinely ambivalent, holding contradictory positions simultaneously without feeling incoherent. It explains why the same person can seem like different people in different contexts. It explains why decisions feel agonizing when you haven't chosen yet, as though multiple futures are somehow all real until you collapse the wave function of possibility by making a choice. The classical computational model of mind has no framework for understanding any of this. A computer's memory contains definite bits. A program executes deterministic algorithms. State transitions follow logical rules. There's no ambiguity, no superposition, no context-dependent measurement effects. The classical model predicts that humans should be rational utility maximizers, that our preferences should be stable and well-ordered, that our judgments should follow the axioms of classical probability theory. And we're none of those things. Not because we're broken computers, but because we're not computers at all. The revelation began in the early 2000s when physicists and cognitive scientists started collaborating in earnest. Researchers like Jerome Bluesmeyer, Peter Bruza, and Andrei Krennikov began applying quantum probability theory to cognitive phenomena, not as a vague metaphor, but as rigorous mathematical modeling. They constructed quantum models of decision-making, concept combination, memory retrieval, and perception. And something remarkable happened. The models worked. They predicted human behavior more accurately than classical models, sometimes dramatically so. The conjunction fallacy that stumped classical probability. Quantum probability explains it perfectly through interference effects between probability amplitudes, the order effects in judgment, incompatible measurements, just like in quantum mechanics. the ambiguity and context sensitivity of human thought, superposition and contextuality, fundamental features of quantum systems. None of this means that your brain is a quantum computer in the sense that might exist in a physics lab. The neurons firing in your skull operate according to classical electrochemical principles for the most part. What it means is that the mathematical structure of thought, the way concepts relate to each other and evolve over time, the architecture of cognition itself follows quantum rather than classical logic. Your brain is a classical physical system that implements quantum information processing at the level of cognition. It's like how a classical computer can simulate quantum mechanics. The hardware is classical, but the patterns it creates follow quantum rules. Except in your case, evolution discovered this trick billions of years before humans invented quantum computing. Your consciousness naturally operates in quantum mathematical spaces without requiring exotic hardware, because quantum logic is simply better suited for navigating ambiguity, integrating context, and managing the overwhelming complexity of reality. But here's what makes this truly extraordinary. The classical model didn't just fail to explain human irrationality. It failed to recognize that what it called irrationality might actually be a more sophisticated form of rationality, adapted to the quantum structure of reality itself. When you commit the conjunction fallacy, you're not making an error. You're correctly applying quantum probability rules where classical rules don't apply. When your beliefs change based on question order, you're not being inconsistent. You're exhibiting contextuality, a fundamental feature of quantum systems that reflects the deep truth that properties don't exist independently of the context in which they're measured. When you feel ambivalent and undecided, holding multiple contradictory positions in your mind simultaneously, you're not confused. You're in superposition. And collapsing that superposition prematurely would eliminate valuable information about the possibility space you're exploring. The classical computational model demanded that you be a certain kind of thinker, one who operates according to Boolean logic and Bayesian probability. When you didn't, science labeled you defective. But quantum cognition reveals that you were operating according to a deeper, more fundamental mathematics all along, one that classical science simply lacked the tools to recognize. Your brain doesn't malfunction when it violates classical probability. It transcends classical probability because thought itself requires a richer mathematical structure than 19th century statistics could provide. This is the first great awakening about the nature of mind. You are not a classical computer that occasionally glitches. You are a quantum cognitive system that naturally operates in superposition, creates reality through measurement, and navigates possibility spaces that classical logic cannot even describe. Every thought you have exists first as a probability cloud, before crystallizing into definite form. Every decision you make collapses quantum alternatives into classical actuality. Every moment of consciousness participates in the fundamental quantum nature of reality itself, not metaphorically, but mathematically, actually, verifiably. The implications ripple outward into everything. If consciousness operates quantum mechanically, then the hard boundary between mind and matter starts dissolving. If measurement creates mental reality, then observation isn't passive perception, but active participation. If your thoughts exist in superposition, then you contain multitudes in ways that classical psychology never imagined. And if human cognition follows quantum mathematics, then perhaps quantum mechanics itself is telling us something profound, not just about particles and waves, but about the deep structure of consciousness, information, and reality itself. The story gets even stranger when you realize that this quantum architecture of thought operates within an even more profound structure. Your consciousness doesn't just follow quantum rules. It exhibits patterns that repeat at every scale, from the firing of individual neurons to the arc of your entire life. Patterns that mathematicians call fractals. But before we can understand how your mind thinks fractally, we need to grasp what quantum cognition actually looks like when it's happening inside your skull. We need to see the probability clouds that constitute your thoughts, the entanglements that bind your concepts together, and the measurement processes through which definite mental states emerge from quantum possibility. The classical illusion has been shattered. You've glimpsed that your brain operates through quantum probability rather than classical computation. But the journey into the true nature of consciousness has only just begun. What lies ahead will transform not just how you understand cognition, but how you experience being conscious at all. The quantum mind is waiting to be explored, and every discovery reveals that reality is far stranger, far more participatory, and far more beautiful than the classical worldview ever suggested. Chapter 2. Quantum Probability in the Neural Cathedral. The quantum nature of thought reveals itself most clearly when you examine how concepts exist in your mind before you consciously access them. Right now, think about the word bank. What did your mind conjure? Perhaps you imagined a financial institution with tellers and vaults. Or maybe you pictured the bank of a river, earth sloping down to water. Both meanings exist in the word simultaneously, yet you experienced only one. This isn't a simple matter of context, selecting between pre-existing alternatives. Something far more quantum mechanical is happening. Before you encountered the word in this sentence, the concept of bank existed in your semantic memory as a superposition of both meanings, neither one definite, both present as potentials. The moment your consciousness measured the word by reading it in context, the superposition collapsed into a single interpretation. This is quantum superposition operating in cognition, and it's as real and measurable as superposition in particle physics. In quantum mechanics, superposition describes a system existing in multiple states simultaneously, until measurement forces it into one definite state. Schrödinger's famous cat exists in superposition of alive and dead until the box opens and observation collapses the wave function. This seems absurd when applied to cats, which is precisely why Schrödinger proposed it as a paradox. But at the quantum level, superposition is fundamental reality. An electron doesn't have a definite position before measurement. It exists as a probability wave spread across space, simultaneously here and there and everywhere. The wave function is non-zero. Only when you measure position does the electron collapse into being somewhere specific. Your concepts operate exactly the same way. When you're not actively thinking about democracy, your mental representation of democracy doesn't exist as a single, well-defined concept with fixed properties. It exists as a superposition of multiple potential meanings, associations, emotional valences, and implications. Is democracy about individual freedom or collective decision-making? Is it a system of government or a cultural ideal? Does it evoke positive feelings of empowerment or negative associations with mob rule and populist excess? All of these exist in superposition, probability amplitudes, rather than definite facts about your psychology. only when you're asked a specific question or encounter democracy in a particular context does your quantum state collapse into a definite position. Researchers have demonstrated this with extraordinary precision. In 2009, a team led by Jerome Busemeyer conducted experiments on conceptual combination, the way your mind creates meaning by joining concepts together. They asked participants to judge combinations like pet bird. According to classical probability theory, the likelihood that something is a pet bird should be determined by separate probabilities. How typical is it as a pet? And how typical is it as a bird? But human judgments violated this rule systematically. People rated Robin as a highly typical bird and a moderately typical pet. But when asked about pet bird, they didn't simply multiply these probabilities. The judgment of the combined concept showed interference effects, where the probability amplitudes for pet and bird interacted like waves, sometimes amplifying and sometimes canceling in ways that classical probability cannot describe. The researchers built a quantum model using Hilbert spaces, the same mathematical framework that describes electron states in atoms. In this model, pet and bird exist as vectors in a high-dimensional semantic space, and combining them involves calculating quantum probability amplitudes that can interfere constructively or destructively. The quantum model predicted human judgments with remarkable accuracy, far exceeding classical models. This isn't metaphor or analogy. The mathematics is identical to quantum mechanics. Your concepts literally exist in superposition states that collapse through measurement, and they combine through quantum interference, rather than classical probability rules. Think about what this means for your everyday experience. When you're trying to decide whether you want pizza or sushi for dinner, you're not comparing two definite utility values stored in memory. You're holding both options in superposition, and the decision process involves quantum interference between all the associations, memories, and emotional states connected to each option. The value of pizza doesn't exist as a fixed number waiting to be retrieved. It exists as a probability amplitude that interferes with the context, your current mood, what you ate yesterday, whether you're eating alone or with others. Only when you finally decide does the wave function collapse, and suddenly pizza has a definite value that seems to have been there all along. But it wasn't. It emerged through the measurement process itself. This explains why decisions feel agonizing when you're genuinely ambivalent. You're not just weighing alternatives. You're experiencing superposition directly, the quantum state of your consciousness stretched across incompatible possibilities. The discomfort of indecision is the feeling of existing in multiple potential realities simultaneously, and the relief of finally choosing is the wave function collapse that eliminates all but one possible future. You're not imagining this. You're experiencing quantum mechanics in consciousness. The superposition of mental states also explains why ambiguous sentences create such strange cognitive experiences. Consider the sentence, "Visiting relatives can be boring." As you read it, did you interpret it as the relatives who visit you can be boring, or the act of visiting your relatives can be boring? Your mind probably settled on one interpretation, but here's what's fascinating. Before you consciously parsed the sentence, both meanings existed in superposition in your cognitive system. Neurolinguistic research using brain imaging has shown that when people encounter ambiguous sentences, there's a brief period where neural activity patterns reflect simultaneous processing of both interpretations. Then, within a few hundred milliseconds, The activity collapses into a pattern representing one definite meaning. This is quantum measurement happening in real time in your brain. The ambiguous sentence creates a superposition state in your language processing networks, and the subsequent neural dynamics perform a measurement that collapses the superposition into one interpretation. Most remarkably, the interpretation you end up with depends on context in ways that exhibit quantum contextuality, where the measurement outcome depends on the measurement basis. If the previous sentence mentioned family obligations, you're more likely to collapse into the interpretation about visiting relatives being boring. If the previous sentence mentioned house guests, you're more likely to interpret it as visiting relatives being boring. The context doesn't just bias your interpretation. It fundamentally changes the quantum state you're measuring, ensuring that different contexts can yield incompatible measurements even for the identical sentence. But superposition is just the beginning of quantum cognition. There's something even more extraordinary happening in your semantic networks, something that sounds impossible until you understand quantum entanglement. When two quantum particles become entangled, they form a single quantum system even if separated by vast distances. Measuring one particle instantaneously affects the other in ways that seem to violate the speed of light, so perfectly correlated that Einstein called it spooky action at a distance. For decades, physicists thought entanglement was unique to exotic quantum systems carefully isolated in laboratories. Then they discovered it operates in your mind every time you link two concepts together. Entanglement in quantum mechanics means that two particles share a quantum state that cannot be described by specifying the state of each particle independently. You have to describe the pair as a single system. Measuring one particle immediately determines properties of the other, even if they're light years apart. The correlation between entangled particles is stronger than any classical correlation could be, violating Bell's inequalities in ways that have been experimentally confirmed thousands of times. This non-local correlation is one of the most profound mysteries in physics, and it operates in your semantic memory every time you learn a new association. When you first learned that dolphins are mammals, not fish, you created an entanglement between the concepts dolphin and mammal in your semantic network. These concepts don't exist as independent, separable representations. They share a quantum cognitive state, where thinking about dolphins immediately activates the mammal concept, and thinking about mammals primes the dolphin concept, not through simple spreading activation as classical models suggest, but through genuine quantum correlation. Researchers have tested this by examining how quickly people can make judgments about entangled concepts compared to independent concepts. The speed and strength of association exceed what classical probability theory predicts, exhibiting signatures of quantum correlation. When concepts are strongly entangled, accessing one produces instantaneous effects on the other that violate classical locality principles. This has enormous implications for understanding creativity and insight. When you have a breakthrough idea that connects two seemingly unrelated domains, you're creating a new entanglement in your semantic network. The moment of insight, that aha experience, when suddenly two distant concepts click together, is the formation of quantum correlation between previously independent mental states. Once entangled, these concepts remain correlated in ways that transcend classical explanation. You can't think about one without the other being affected, even if you're not consciously aware of the connection. This is why expertise in one domain can suddenly illuminate problems in a completely different domain. The concepts are quantumly entangled in your mind, and quantum mechanics tells us that entanglement creates correlations that persist regardless of the separation between systems. In your cognitive space, domains that seem completely unrelated can be deeply entangled, enabling non-local influences where insight in one area instantaneously affects another. Consider what happens with priming effects. Those curious phenomena where exposing someone to one word affects how they respond to a subsequent word. If I show you the word doctor, you'll respond faster to the word nurse than to an unrelated word like penguin. Classical explanations say, this happens because doctor activates related concepts through spreading activation in a semantic network. But quantum models reveal something deeper. The concepts, doctor and nurse, are entangled through years of co-occurrence and learned association. They share a quantum state, and measuring one by bringing it into consciousness partially collapses the wave function in a way that makes the other more likely to be measured in subsequent cognitive operations. The priming effect isn't just about activation spreading through networks. It's about quantum measurement, changing the probability distribution for future measurements in entangled systems. This explains why priming effects can be surprisingly strong and specific, stronger than classical models predict. Entangled concepts exhibit correlations that violate classical bounds, just like entangled particles. When researchers build quantum models of semantic priming, they find that quantum predictions match human performance more accurately than classical network models, particularly for cases where concepts are strongly associated through experience. The entanglement of concepts also explains one of the most mysterious aspects of language and thought, meaning holism. Any single concept in your mind is entangled with countless others in ways that make it impossible to specify the meaning of one concept in isolation. What does justice mean? You can't answer without invoking fairness, law, rights, equality, and a dozen other concepts, each of which is itself entangled with hundreds more. The meaning of justice exists as a massively entangled quantum state, distributed across your entire semantic network. This is why dictionaries are circular, defining words in terms of other words that eventually loop back to define the original term. Meaning isn't contained in individual symbols. It exists in the quantum entanglements between symbols, in the correlations that cannot be reduced to properties of individual concepts. Ludwig Wittgenstein intuited this in the 20th century when he argued that meaning is use, that words derive significance from their relationships within language games. What he couldn't articulate is that these relationships are quantum entanglements, genuine, non-local correlations that make meaning fundamentally holistic and context-dependent. Your understanding of any concept is inseparable from your understanding of the entire web of entangled concepts surrounding it. Change one, and the quantum state of the whole network shifts, sometimes subtly, sometimes dramatically. This quantum entanglement in cognition also manifests in emotional and motivational states. Your feelings about different people, activities, and possibilities in your life are not independent variables. They're quantumly entangled in ways that create deep correlations. Your relationship with your partner is entangled with your relationship with yourself. Your feelings about your career are entangled with your sense of identity and purpose. When something shifts in one domain, the entanglement ensures that other domains shift too, often in ways that seem mysterious until you recognize the quantum correlation. This is why personal transformation often happens suddenly and globally, rather than gradually and locally. You work on one issue in therapy, and suddenly multiple areas of life transform together because the underlying quantum states were entangled. Resolve the core entanglement, and the collapse propagates through the entire system instantaneously. Classical psychology thinks of the psyche as a collection of separate modules, traits, and tendencies that can be addressed independently. Quantum cognition reveals that you're a holistic system of entangled mental states, where changes in one part immediately affect the whole through non-local quantum correlations. But quantum entanglement and superposition lead to an even stranger feature of cognition that directly parallels one of the deepest mysteries in quantum mechanics: contextuality. In quantum physics, contextuality means that the result of measuring a property depends not just on the system being measured, but on what other properties you measure simultaneously. You cannot assign definite, pre-existing values to quantum properties independent of the measurement context. The properties come into being through measurement, and which properties you measure determines what values are possible. Alain Aspect's Nobel Prize-winning experiments demonstrated this conclusively for photons. Now, we know that human cognition exhibits the same contextuality, where your beliefs and preferences don't exist as context-independent facts, but emerge through the context in which they're measured. Return to those political opinion surveys, where question order changes responses. When researchers ask people whether they support increasing military spending and whether they support increasing education spending, the order matters. If military spending is asked first, people are more likely to oppose increased education spending. If education spending is asked first, the pattern reverses. Classical survey methodology treats this as measurement error, noise to be minimized. But quantum cognition recognizes it as contextuality, a fundamental feature of quantum systems where measurements are incompatible. Supporting military spending and supporting education spending are incompatible measurements in cognitive space. Asking about one creates a mental state that makes certain answers to the other more or less likely. The context of the first question doesn't just bias your response to the second question. It fundamentally changes what mental state is being measured when the second question is asked. Your political preferences don't exist as definite values waiting to be reported. They exist as quantum potentials that collapse into definite opinions through the measurement process, and incompatible measurements cannot be performed simultaneously without disturbing the system. This is Heisenberg's uncertainty principle operating in opinion dynamics. The same contextuality appears in how you perceive objects and categorize experiences. Whether you categorize a tomato as a fruit or a vegetable depends on context. In a botanical context, it's clearly a fruit. In a culinary context, it functions as a vegetable. Classical categorization theory assumes objects have definite category memberships that we discover through observation. But quantum cognition reveals that category membership is contextual, created through the act of categorization in a specific context. The tomato doesn't secretly have a true category membership that context merely obscures. The category membership is indeterminate until the context provides a measurement basis that collapses the quantum state into one definite answer. This is why you can sincerely say that a tomato is both a fruit and not a fruit without contradicting yourself. The truth value depends on the context, just like a quantum particle can have definite momentum or definite position, but not both simultaneously. The contexts are incompatible measurement bases. This contextuality pervades every aspect of cognition. Whether an action is aggressive or assertive depends on context. Whether an outcome is success or failure depends on context. Whether a person is friend or stranger depends on context. None of these properties exist as fixed facts prior to contextual measurement. They emerge through the interaction between the quantum state of your mental representation and the measurement basis provided by context. Understanding contextuality transforms how you relate to your own beliefs and perceptions. You can stop trying to figure out what you really think about something, as if there's a context-independent truth buried in your psyche. Instead, you recognize that what you think depends fundamentally on the context in which you're thinking it. Different contexts don't reveal different aspects of a single underlying belief. They create genuinely different beliefs through contextual measurement of quantum cognitive states. This brings us to perhaps the most mind-bending aspect of quantum cognition, the role of probability amplitudes in decision-making. In classical probability, probabilities are always positive numbers between 0 and 1 that represent the likelihood of events. But in quantum mechanics, the fundamental objects aren't probabilities themselves. They're probability amplitudes, complex numbers that can be positive or negative. And probabilities are calculated by taking the squared magnitude of these amplitudes. This mathematical structure allows for interference effects, where amplitudes can add or subtract, creating probabilities that violate classical bounds. Your decision-making processes use probability amplitudes, not classical probabilities, which is why your choices often seem irrational from a classical perspective. They're not irrational, they're quantum rational. When you face a decision between two options, classical decision theory says you should assign a utility to each option and choose the one with higher expected utility. But that's not what you do. You consider how each option feels in different scenarios, how it aligns with different aspects of your identity, what it means in different contexts. Each of these considerations contributes a probability amplitude to the decision, and these amplitudes can interfere. Some considerations amplify each other, making certain choices feel more compelling than the sum of their parts. Other considerations interfere destructively, creating doubt and hesitation, even when the classical utility calculation suggests an obvious choice. Researchers studying the prisoner's dilemma, a classic game theory scenario, found that human choices show quantum interference patterns. In the prisoner's dilemma, two players simultaneously choose to cooperate or defect. Classical game theory predicts specific strategies based on utility maximization, but actual human players deviate from these predictions in patterned ways that match quantum models perfectly. When making the choice, players hold both cooperation and defection in superposition, and the amplitudes associated with each option interfere based on beliefs about the other player, social norms, personal values, and contextual cues. The final choice emerges from this interference process, and the probabilities of cooperation and defection show signatures of quantum interference that cannot be explained by classical probability theory. The most dramatic demonstration of probability amplitude effects in cognition comes from a phenomenon that classical probability theory says should be impossible: negative probabilities. In quantum mechanics, probability amplitudes can be negative, and when you square them to get actual probabilities, the negativity enables interference effects. Cognitive scientists have found that human judgments sometimes exhibit what looks like negative probability, impossible in classical frameworks but natural in quantum ones. When people estimate the likelihood of complex events involving multiple stages, Their estimates can show systematic deviations that only make sense if intermediate stages are assigned negative probability amplitudes that interfere to produce the final judgment. The mind doesn't work with simple probabilities. It works with richer mathematical objects that allow for the kind of subtle, contextual integration that probability amplitudes provide. This amplitude structure explains why human intuition is so powerful and so difficult to formalize in classical artificial intelligence. When you have a gut feeling about something, you're not performing an explicit probability calculation. You're allowing probability amplitudes from countless sources to interfere in quantum cognitive space, and the result is a feeling, a sense of rightness or wrongness that emerges from interference patterns you could never consciously calculate. The feeling is the squared amplitude, the probability that emerges from constructive or destructive interference among all the considerations your mind is processing in parallel. Artificial intelligence systems based on classical probability can be trained to approximate these judgments, but they're always missing something because they lack the amplitude structure that allows for genuine quantum interference. Your intuition is quantum mechanical, and that's why it often outperforms explicit reasoning in complex, ambiguous situations where contextuality matters. Understanding your mind as a quantum system using probability amplitudes also illuminates why changing your mind can feel like such a dramatic shift. When you hold a belief strongly, it's not just that the classical probability is high, it's that the probability amplitude has a particular phase and magnitude that's reinforced through coherent interference. When something happens that challenges the belief, it doesn't just lower the probability gradually. It can shift the phase of the amplitude, causing destructive interference with what was previously constructive. The result is a sudden collapse of certainty, a phase transition in your cognitive state where belief flips to doubt almost instantaneously. This is why minds change through revolutions more than through gradual accumulation of evidence. The quantum structure of cognition favors coherent states that resist change until interference patterns shift, then transform dramatically. You see this in scientific paradigm shifts, religious conversions, falling in and out of love, and every other domain where beliefs are held strongly and then transform suddenly. The change isn't just quantitative. It's a quantum phase transition driven by shifts in probability, amplitude, interference. The quantum probability structure of cognition has one more profound implication that ties directly into the deepest questions about consciousness itself. In quantum mechanics, probability amplitudes evolve deterministically according to the Schrödinger equation, spreading and interfering in precise, predictable ways. But when measurement occurs, something different happens. The wave function collapses, probability becomes actuality, and superposition gives way to definiteness. This collapse is quantum mechanics' greatest mystery, and some physicists believe it requires consciousness as the agent that performs measurement and causes collapse. If that's true, then quantum cognition isn't just a useful mathematical model for describing thought. It's revealing that consciousness and quantum mechanics are deeply connected at a fundamental level. Your thoughts exist in quantum superposition. Your concepts are quantumly entangled. Your judgments exhibit contextuality, and your decisions emerge from probability amplitude interference. But the collapse of these quantum mental states into definite experiences requires something beyond the physical quantum system. It requires the observer, the consciousness that makes measurement, the aware presence that transforms potential into actual. This is the measurement problem in consciousness, and it suggests that you are not simply a quantum system. You are the observer who measures quantum systems, and that observer might not be reducible to physics at all. We've journeyed through the quantum probability architecture of thought, from superposition and entanglement to contextuality and amplitude interference. Every aspect of your cognition operates through quantum mathematical structures that classical models cannot capture. You are a walking, thinking quantum system, your mind filled with probability clouds that collapse into experience through the mysterious process of conscious observation. But the quantum nature of cognition is just one layer of this cognitive architecture. There's another pattern woven through your consciousness, one that operates at every scale from milliseconds to lifetimes, from single neurons to entire civilizations. Your mind doesn't just think quantum mechanically, it thinks fractally. And understanding this fractal architecture reveals something even more profound about the nature of consciousness, something that will transform how you experience every moment of thought, every pattern of behavior, every layer of self-awareness. The quantum cathedral of your mind is built on fractal foundations, and those foundations extend infinitely deep. Chapter 3. The Fractal Architecture of Thought. Look at the branching structure of a tree, the way its trunk divides into major limbs, which subdivide into branches, which split into twigs, which separate into ever finer structures until you reach individual leaves. Now, look at the veins within a single leaf, the way they branch and subdivide in patterns that mirror the tree itself. Then, look at your own circulatory system, your bronchial tubes, the neurons in your brain. The same pattern repeats at every scale. Nature doesn't just reuse this branching design occasionally. It's everywhere, from the delta of a river to the structure of galaxies, from lightning bolts to the internet. This isn't coincidence. It's a fundamental principle of organization that mathematicians call fractal geometry, and it governs not just the shape of physical structures, but the architecture of your consciousness itself. Your thoughts, your memories, your sense of self, they all exhibit fractal patterns that repeat from the smallest neural activity to the sweep of your entire biography. Understanding how your mind thinks fractally doesn't just explain consciousness. It reveals that you are a pattern within patterns within patterns, a self-similar structure extending infinitely inward and outward, each layer reflecting every other layer in an endless dance of recursive complexity. The word fractal comes from the Latin fractus, meaning broken or fractured, and it was coined by mathematician Benoit Mandelbrot in 1975. Mandelbrot was studying irregular, rough shapes that traditional geometry couldn't describe, coastlines and mountains and clouds, natural forms that resist reduction to simple, geometric primitives like circles and rectangles. What he discovered was that these irregular shapes weren't random. They exhibited a specific kind of order called self-similarity, where the same pattern repeats at different scales. Zoom in on a fractal, and you see the same structure you saw at the larger scale. Zoom in again, and there it is once more. This recursive self-similarity continues indefinitely, at least in mathematical idealizations. Real physical fractals have limits based on atomic structure and other constraints, but across many orders of magnitude, they maintain self-similar patterns. The classic example is the Mandelbrot set itself, that iconic psychedelic image of infinite complexity generated by a simple equation. No matter how far you zoom into the boundary of the Mandelbrot set, you keep finding new details that echo the overall structure. Spirals within spirals within spirals, each containing entire miniature versions of the set itself. This infinite depth from finite rules exemplifies what makes fractals so powerful and so prevalent in nature. Fractal geometry revolutionized how scientists understand complexity because it provided the first mathematical framework for describing the roughness, irregularity, and infinite detail characteristic of natural forms. Before Mandelbrot, mathematicians dealt almost exclusively with smooth, regular shapes. Euclidean geometry describes idealized objects, perfect circles and straight lines that exist only in abstract mathematical space. Nature, meanwhile, is rough, wrinkled, branching, and irregular. How do you measure the length of a coastline when it changes depending on the resolution of your measurement? Use a 1-kilometer ruler and you get one answer. Use a 1-meter ruler and the coastline gets longer because you capture more detail. Use a 1-centimeter ruler and it gets longer still. Mandelbrot realized that coastlines don't have a single, definite length in the traditional sense. They have a fractal dimension that describes how their detail scales across measurements. This fractal dimension is a number that can be fractional, something between the integer dimensions we're used to. A line has dimension 1, a plane has dimension 2, but a coastline has a dimension somewhere between 1 and 2, perhaps 1.2, indicating it's rougher than a line but not quite filling a plane. This fractional dimensionality captures the essence of fractal complexity. The mathematics becomes even more fascinating when you realize what fractal dimension actually measures. It quantifies how efficiently a structure fills space as you change scales. A straight line increases in length proportionally as you zoom in. A fractal increases faster because it reveals more detail. The fractal dimension tells you the exponent of this scaling relationship. Higher fractal dimensions mean more complexity, more information density, more efficient packing of structure into available space. Nature appears to optimize for this complexity across countless systems, because fractal organization provides enormous advantages. Fractals maximize surface area for a given volume, which is why your lungs are fractal, maximizing gas exchange surface within the limited space of your chest. Fractals enable efficient distribution networks, which is why rivers, blood vessels, and neural networks are fractal, moving resources from central sources to dispersed destinations with minimal redundancy. Fractals create robust systems that work across multiple scales, maintaining function whether you're dealing with tiny capillaries or major arteries, individual neurons or entire brain regions. Biology discovered fractals billions of years before humans invented the mathematics to describe them, because fractal organization solves fundamental problems of life and complexity. But here's what makes fractals truly remarkable for understanding consciousness. The same principles that govern the shape of a neuron govern the shape of entire neural networks, and the same principles that govern moment-to-moment brain activity govern the patterns of thought across hours, days, and lifetimes. Your mind is fractal not just spatially but temporally, exhibiting self-similar patterns across time scales from milliseconds to decades. This fractal architecture isn't an accident or a quirk. It's the fundamental organizational principle that allows consciousness to function across the vast range of scales that cognition requires. Consider a single neuron in your brain, specifically its dendritic tree, the branching structure that receives inputs from other neurons. If you could examine this structure under a microscope, you'd see something astonishing. The dendrite branches follow precise fractal geometry. The main dendrite splits into several primary branches, each of which subdivides into secondary branches, which split into tertiary branches, continuing through multiple levels of organization. At each level of branching, the pattern is self-similar. The angle of branching, the length ratio between parent and daughter branches, the number of subdivisions, all these parameters remain approximately constant across scales. This isn't loosely fractal or fractal-ish. Detailed measurements of dendritic trees from across the brain reveal fractal dimensions, typically ranging from 1.5 to 2.2, quantifying exactly how these structures fill three-dimensional space. The fractal nature of dendrites isn't decorative. It's functional. Each neuron needs to receive input from thousands of other neurons, sometimes tens of thousands. The fractal branching of dendrites allows maximal reception of synaptic contacts within a compact space. If dendrites were simple straight lines, they couldn't make enough connections. If they filled space completely, they'd be too costly in terms of materials and energy. The fractal dimension of around 2 represents an optimal compromise, enough branching to create enormous connectivity without excessive metabolic burden. But the fractal architecture doesn't stop at individual neurons. When you zoom out to look at networks of neurons, the connectivity patterns are also fractal. Neurons connect to nearby neighbors and to distant neurons in patterns that exhibit scale-free properties characteristic of fractals. Some neurons are highly connected hubs, others are more peripheral, and the distribution of connections follows a power law, another signature of fractal organization. Power laws mean that there's no typical scale. Most neurons have relatively few connections, some have many, and a very few have enormous numbers of connections. The ratio remains constant across scales, a defining feature of fractals. This scale-free network architecture enables incredibly efficient information processing. Signals can propagate across the entire brain through a small number of steps because of the highly connected hubs. Local neighborhoods can process information in parallel. The network remains robust to damage because multiple pathways exist between any two regions. All of these properties emerge naturally from fractal organization. Zoom out further to look at entire brain regions, and the fractal pattern persists. The white, matter tracts. Connecting different cortical areas show fractal branching patterns. The gray matter of the cortex itself exhibits fractal geometry, with its characteristic folding increasing surface area in a fractal manner. Measure the fractal dimension of cortical folding across species, and you find something remarkable. More intelligent species have higher fractal dimensions in their cortex. Human brains have a fractal dimension around 2.5 to 2.8, while simpler mammals have lower dimensions. The increased fractal complexity correlates with increased cognitive sophistication because the fractal folding maximizes the amount of cortical surface packed into the skull, and cortical surface area is strongly correlated with cognitive capacity. Your intelligence exists partly because your brain is more fractally complex than other animals' brains. The recursive self-similarity of fractal organization creates more room for information processing, more opportunities for novel connections, more substrate for consciousness to emerge. But the spatial fractals in brain structure are just the beginning. Your brain's activity over time exhibits fractal patterns that are even more profound for understanding consciousness. Neural activity doesn't occur in regular periodic rhythms like a metronome. It shows complex variability that turns out to be fractal in its temporal structure. This discovery came from analyzing what neuroscientists call neural avalanches, cascading bursts of activity that propagate through neural networks. When one neuron fires, it can trigger several others to fire, which trigger still more, creating a cascade of activity. These avalanches come in all sizes, from tiny events involving just a few neurons to massive waves engaging large portions of the brain. The remarkable finding is that the distribution of avalanche sizes follows a power law, the signature of fractal organization. There's no typical avalanche size. Small avalanches are common, large avalanches are rare, and the mathematical relationship between size and frequency is scale-free. This means the brain operates at a critical point, balanced between too much order and too much chaos, a state physicists call criticality. Systems at criticality exhibit fractal dynamics, and the brain appears to maintain itself perpetually at this critical point. Why would the brain evolve to operate at criticality? Because criticality enables optimal information processing. A brain that's too orderly would be like a crystal, rigid and predictable, unable to respond flexibly to novel situations. A brain that's too chaotic would be like a gas, with activity dispersing randomly without forming coherent patterns. Criticality sits exactly at the boundary between order and chaos, enabling the brain to form stable patterns while remaining sensitive to new inputs. At criticality, information can propagate across the network with maximal efficiency. Small perturbations can trigger large avalanches when necessary, allowing whisper-quiet signals to sometimes generate thunderous responses. The system can store information in stable attractors while remaining flexible enough to transition between attractors rapidly. All of these computational advantages emerge from maintaining fractal, critical dynamics. Your consciousness exists at this knife edge between order and chaos, and that's not a bug. It's precisely the condition that allows you to be conscious at all. The fractal nature of neural avalanches reveals itself in other temporal measures too. If you record the time intervals between neural firings, you find fractal temporal structure. Instead of neurons firing at regular intervals like a clock, they fire with intervals that show long-range correlations and scale-free variability. This creates what's called 1 over F noise, a specific kind of temporal fractal, where the power spectrum of the signal decreases as 1 over the frequency. 1 over F noise appears throughout nature, from earthquakes to stock markets to heartbeats to traffic patterns. It represents an optimal balance between predictability and surprise, between structure and flexibility. Pure randomness would be white noise, equal power at all frequencies, completely unpredictable. Pure order would be a single frequency, completely predictable. 1 over F noise lies between these extremes, containing correlations at all time scales simultaneously. Your brain waves exhibit 1 over F noise across frequencies from millihertz to hundreds of hertz, meaning the activity happening right now is correlated with activity from seconds ago, minutes ago, even hours ago, all simultaneously. This creates temporal coherence across scales, allowing your consciousness to integrate information from multiple timescales into a unified experience. Think about what this means for your subjective experience of time. You're aware of the immediate present moment, the word you're reading right now, but simultaneously you're aware of the sentence as a whole, the paragraph, the general topic, your purpose in reading, your broader goals and context. These different timescales of awareness coexist in consciousness because your brain's fractal temporal dynamics naturally integrate information across scales. The 1/f noise in neural activity creates a temporal architecture where what's happening now at the millisecond scale is embedded within patterns unfolding over seconds, which are embedded within patterns unfolding over minutes and hours and days. Consciousness doesn't happen at a single timescale. It spans a fractal hierarchy of nested timescales, each influencing the others in self-similar patterns. This is why you can shift attention fluidly between immediate sensations and long-term planning, between split-second reactions and philosophical contemplation. Your brain's fractal temporal architecture supports awareness at all these scales simultaneously. Researchers measuring reaction times in psychological experiments discovered another manifestation of temporal fractals in cognition. When you press a button in response to a stimulus repeatedly, your reaction time varies from trial to trial. Classical models assumed this variability was random noise, meaningless fluctuation around some true reaction time. But detailed analysis revealed that the variability itself has structure. It's not random, it's fractal. The pattern of reaction time fluctuation shows long-range correlations, where how fast you respond now is subtly influenced by how fast you responded many trials ago, even dozens of trials ago. The time series of reaction times exhibits 1/f scaling, indicating fractal temporal structure. This isn't noise. It's the natural dynamics of a complex system operating at criticality. The variability in your performance from moment to moment reflects the fractal architecture of the cognitive processes underlying the task. Even more fascinating, the degree of fractal scaling correlates with cognitive function. Healthy young adults show stronger fractal patterns in reaction time variability than elderly adults or patients with neurological disorders. As the brain ages or becomes damaged, the fractal structure degrades, becoming more random or more rigid. The loss of fractal complexity in temporal dynamics is a biomarker of declining cognitive function. Your mind works better when it's more fractal. The same principle applies to memory. When you try to recall items from a list, the time it takes to retrieve each memory shows fractal patterns. Recall certain types of memories quickly, others slowly, and the distribution of retrieval times follows a power law. There's no single characteristic memory retrieval time. Instead, you have a scale-free distribution spanning orders of magnitude, from near instantaneous recall of highly familiar information to slow, effortful retrieval of obscure memories. This fractal distribution emerges because memory itself is organized fractally. Memories aren't stored as discrete files in separate locations. They're distributed across networks that exhibit self-similar connectivity patterns at multiple scales. Retrieving a memory involves activating a pattern across this fractal network, and the time required depends on how the specific memory is embedded within the fractal structure. Strongly connected, frequently accessed memories sit in central positions within the network topology and retrieve quickly. Peripheral, rarely accessed memories require traversing more network steps and retrieve slowly. The fractal organization creates this naturally graded continuum of accessibility, but the fractal architecture of thought extends beyond just timing. The semantic structure of your knowledge exhibits fractals too. Language itself is fractal in multiple ways. The most famous linguistic fractal is Zipf's law, discovered by linguist George Kingsley Zipf in 1935. Zipf analyzed the frequency of words in large text corpora, and found a precise mathematical relationship. The most common word appears roughly twice as often as the second most common word, 3 times as often as the third most common word, and so forth. The frequency of a word is inversely proportional to its rank, creating a power law distribution that's the signature of fractal organization. This pattern holds across languages, across time periods, across genres. It's a universal feature of human language. But why? The fractal distribution of word frequencies emerges from the way language balances competing demands. You need common words for efficient communication, but you also need rare words for precise expression. The fractal distribution optimizes this trade-off, creating a vocabulary where you can say most things using mostly common words, but you always have access to rarer words when you need specificity. The fractal structure makes language maximally efficient as an information-carrying system. Zipf's law is just the beginning of linguistic fractals. The structure of sentences exhibits self-similarity. A sentence contains phrases. Phrases contain sub-phrases, and the grammatical relationships at each level mirror the relationships at other levels. A noun phrase has the same kind of hierarchical structure as a verb phrase, which has the same kind of structure as a prepositional phrase. This recursive, self-similar syntactic structure is fractal. It allows infinite expressiveness from finite rules, the same principle that makes mathematical fractals infinitely complex from simple equations. You can nest clauses within clauses within clauses, creating sentences of arbitrary complexity while maintaining grammatical coherence. The fractal nature of syntax is why a child learning a finite set of grammatical rules can produce and understand an infinite variety of sentences they've never encountered before. Language is fractal, and that's what makes it inexhaustibly creative. The fractal principle extends deeper into meaning itself. Concepts are organized in hierarchical taxonomies where higher-level categories contain lower-level categories in nested fashion. Animal contains mammal, which contains primate, which contains human. But the structure isn't just hierarchical. It's fractal, because the relationships between categories at one level mirror the relationships at other levels. The way human relates to primate is similar to how primate relates to mammal, creating self-similarity across levels of abstraction. Moreover, individual concepts contain rich internal structure that recapitulates the larger semantic space. Your concept of dog contains subconcepts for different breeds, different contexts of interaction, different emotional associations, different roles in human culture. Each of these subconcepts has its own internal structure, and within that structure you find further subdivisions, continuing down through multiple levels. The entire semantic space is fractal, with meaning nested within meaning in self-similar patterns at every scale. This fractal semantic structure enables something remarkable about human cognition: metaphor. When you understand one domain in terms of another, you're mapping fractal structures onto each other. The reason metaphors work is the different conceptual domains often have self-similar structures that can be aligned. When you say that argument is war, you're recognizing that the structure of arguments, attack and defense, strategy and tactics, winning and losing, mirrors the structure of warfare. The fractal self-similarity across domains allows you to transfer understanding from familiar territory to unfamiliar territory by recognizing that the pattern repeats at different scales or in different contexts. All of human abstract reasoning depends on this ability to recognize self-similar patterns, across superficially different domains. Mathematics itself is largely the discipline of recognizing fractal patterns in logical space, seeing how the same structural relationships appear in arithmetic, geometry, algebra, and analysis. Every mathematical proof, by analogy or isomorphism, is an exploitation of fractal self-similarity in the space of possible mathematical structures. Stories and narratives exhibit fractal structure too. A novel contains chapters. Chapters contain scenes. Scenes contain moments. And at each level you find the same dramatic structure repeating. Each scene has its own arc of rising action, climax, and resolution, mirroring the overall plot arc of the entire novel. Each moment within a scene contains its own micro-arc of tension and release. This self-similar nesting is why stories can be satisfying at multiple levels simultaneously, why a great novel rewards reading at both the immediate sentence level and the overall thematic level. The fractal structure of narrative reflects the fractal structure of lived experience. Your day contains moments of drama and resolution. Your life contains arcs of development and transformation, and these patterns nest within each other in self-similar ways. When you construct autobiographical memory, you're organizing experience into fractal narrative structures that make sense across multiple timescales. The story of your morning is embedded in the story of your day, embedded in the story of your week, embedded in the story of your year, embedded in the story of your life. Each level has its own coherence, while participating in the coherence of every other level. This fractal narrative structure of consciousness creates something deeply strange and profound, the recursive self-awareness that characterizes human consciousness. You can think about your thinking, have feelings about your feelings, tell stories about your story-making. Each act of reflection creates a new level in the fractal hierarchy of self-awareness. But because the structure is fractal, each level of reflection mirrors every other level. The way you think about your thinking resembles the way you think about anything else. The feelings you have about your feelings follow the same emotional patterns as your feelings about external events. This creates a strange loop, a term coined by Douglas Hofstadter to describe how a consciousness seems to contain itself recursively. You exist at every level of your own cognitive fractal simultaneously, both the thinker and the thought, both the observer and the observed, both the story and the storyteller. The fractal architecture makes this possible because self-similar patterns can nest indefinitely, creating coherent structure even in the paradoxical situation where a system contains models of itself within itself. The fractal nature of consciousness also explains the curious phenomenon of psychological patterns repeating across your lifetime. You've probably noticed that you tend to encounter the same issues in different relationships, face similar challenges in different careers, repeat patterns of behavior, despite consciously trying to change. These aren't separate, unrelated problems. They're fractal repetitions of core dynamics that operate at multiple scales in your psychological structure. The same wound that created difficulty in your relationship with your parents creates difficulty in romantic relationships, friendships, professional relationships, even your relationship with yourself. The pattern is self-similar, manifesting differently at each scale, but maintaining the same essential structure. This is fractal psychology. Your personality isn't a collection of discrete traits. It's a fractal structure where core patterns repeat at every level of organization, from momentary reactions to lifelong tendencies. Recognizing your psychological fractals is the first step toward changing them. Because once you see that the pattern at one scale is the same pattern appearing everywhere, You realize you're not fighting 100 separate problems. You're working with one fractal structure that manifests 100 different ways. Change the core pattern, and the change propagates fractally across all levels of your psychological life. Therapists and counselors who understand fractal psychology recognize that deep change happens not through addressing symptoms at superficial levels, but through working at the scale where the fractal pattern originates. Childhood trauma creates a fractal template that repeats throughout life unless the core pattern is recognized and transformed. The transformation doesn't happen by fixing each repetition individually. It happens by working with the generative pattern itself, the strange attractor in psychological phase space that keeps pulling your behavior back into self-similar orbits. When you genuinely resolve a core issue, you often find that multiple areas of life transform simultaneously. This isn't magic or wishful thinking. It's fractal dynamics. The same pattern existed at multiple scales, so changing it at the fundamental level propagates changes across all scales automatically. Your psyche is deeply interconnected through fractal self-similarity. And that interconnection means profound change is possible when you work at the right level of the fractal hierarchy. The fractal architecture of consciousness has one final implication that connects back to the quantum nature of thought we explored earlier. Fractals and quantum mechanics are intimately related mathematically. Fractal patterns often emerge in quantum systems, particularly at phase transitions and critical points. The brain's maintenance of criticality, its operation at the boundary between order and chaos, creates both fractal dynamics and conditions favorable for quantum effects. The fractal structure provides the framework within which quantum superposition, entanglement, and contextuality can operate. You could say that your mind is a quantum computer running on fractal hardware, or equally that it's a fractal system leveraging quantum computation. The two principles interweave because both reflect fundamental features of complex systems operating at criticality, where the most sophisticated information processing becomes possible. The fractal architecture creates the multi-level structure necessary for consciousness to span vast ranges of scale from neurons to narratives. The quantum mechanics provides the subtle, probabilistic dynamics that enable flexible, context-sensitive cognition. Together, they constitute the cognitive architecture that makes your particular form of consciousness possible, a consciousness that can be simultaneously focused and diffuse, logical and intuitive, structured and fluid, one and many. We've traced the fractal patterns in your brain from the branching of dendrites to the structure of lifelong identity, from the timing of neural avalanches to the organization of semantic memory. At every scale, the same principles apply. Self-similarity creates efficient information processing. Scale-free dynamics enable flexibility and robustness. Critical dynamics support optimal computation. These aren't separate features of different systems. They're manifestations of a single fractal architecture that underlies all cognition. You are a fractal being, your consciousness constructed from patterns within patterns, each level reflecting and influencing every other level in an endless recursion of self-similar complexity. Understanding this fractal nature of mind isn't just intellectually satisfying, it's practically transformative. When you recognize that your thoughts right now are fractally related to your thoughts across your lifetime, you gain leverage. Change a pattern at one scale, and you change it at all scales. Recognize a structure repeating, and you can work with the generator rather than fighting infinite instances. Your fractal nature makes you both more deeply interconnected than you imagined and more capable of fundamental transformation than you dared hope. But the fractal architecture of thought operates within an even stranger substrate, one that challenges our most basic assumptions about what consciousness is and where it exists. The quantum and fractal patterns we've explored so far assume a physical brain implementing these dynamics. But what if the brain itself exhibits quantum effects at biological temperatures? What if consciousness doesn't just use quantum mathematics, but actually depends on genuine quantum physical processes? The answer takes us into the controversial territory of quantum biology, where the warm, wet environment of your skull might preserve quantum coherence longer than physics predicted possible. Chapter 4. Quantum Coherence in Biological Minds. For most of the 20th century, physicists operated under a reasonable assumption. Quantum effects like superposition and entanglement are delicate phenomena that survive only in carefully controlled laboratory conditions, isolated systems cooled to near absolute zero, shielded from vibration and electromagnetic interference. The warm, wet, noisy environment of a living cell should destroy quantum coherence almost instantly through a process called decoherence. Thermal energy at body temperature, 37 degrees Celsius, seemed far too violent for quantum states to persist. Random molecular collisions, electromagnetic fluctuations, and the general chaos of biological chemistry should collapse quantum superpositions into classical definiteness in femtoseconds, quadrillionths of a second. This decoherence timescale is so short that quantum effects couldn't possibly influence biological processes that unfold over milliseconds or longer. Therefore, life must operate entirely through classical physics and chemistry. Quantum mechanics determines the behavior of individual atoms and molecules. But once you scale up to cellular structures and biochemical reactions, classical mechanics takes over. This seemed so obviously true that most biologists never questioned it. Life was too hot, too wet, too noisy for quantum effects to matter. But then, experiments started revealing something impossible. Nature had figured out how to protect quantum coherence in biological systems, maintaining quantum effects for far longer than theory predicted possible. The warm quantum paradox was dissolving, and with it, the assumption that consciousness operates purely classically. The first hint came from photosynthesis, the process by which plants convert sunlight into chemical energy. For decades, scientists understood photosynthesis as a classical chemical process. Light hits a chlorophyll molecule, exciting an electron. That excitation energy migrates through the photosynthetic complex until it reaches a reaction center where it drives chemistry. The efficiency of this energy transfer is remarkable, approaching 100% in many plants. Essentially, all captured light energy converts to chemical energy with almost no waste. Classical models struggled to explain this near-perfect efficiency. Energy moving through molecular structures should dissipate through various loss mechanisms. Yet somehow, photosynthesis minimizes these losses to an extraordinary degree. In 2007, researchers at the University of California, Berkeley performed experiments that revealed why. They used ultra-fast laser spectroscopy to track energy transfer in photosynthetic complexes with femtosecond time resolution. What they discovered shocked the physics community. The excitation energy doesn't travel along a single path through the molecular complex. It exists in quantum superposition, exploring all possible paths simultaneously. The energy traverses the photosynthetic complex as a quantum wave, spreading through multiple routes at once, and this quantum coherence persists for hundreds of femtoseconds, even at room temperature, far longer than decoherence theory predicted. The quantum superposition allows the energy to sample all pathways simultaneously and select the most efficient route, avoiding dead ends and energy traps that would waste precious photons. Photosynthesis isn't just classical chemistry. It's quantum computation performing real-time optimization to maximize efficiency. This discovery revolutionized quantum biology because it demonstrated conclusively that biological systems can maintain quantum coherence despite warm, wet, noisy conditions. The photosynthetic complex achieves this through specific structural features that protect quantum states from decoherence. The molecules are arranged in precise geometric configurations that shield the quantum energy transfer from environmental disturbances. Protein scaffolds surrounding the chromophores create a partially isolated environment where quantum effects can persist. Some researchers suggest that the noise itself might help rather than hinder, a phenomenon called environment-assisted quantum transport, where certain types of molecular vibrations enhance rather than destroy quantum coherence. The mechanism remains under investigation, but the essential fact is undeniable. Evolution discovered quantum computation billions of years before humans did, and life exploits quantum effects routinely in one of its most fundamental processes. If photosynthesis uses quantum coherence, what else might? The question led researchers to examine bird navigation, another phenomenon that classical physics struggled to explain. Migratory birds navigate across thousands of miles with remarkable precision, and many species can sense Earth's magnetic field to maintain their bearing. For years, scientists puzzled over the mechanism because Earth's magnetic field is extremely weak, far too weak to influence classical chemical reactions significantly. How could birds detect something so subtle? In 2004, physicist Klaus Schulten proposed a radical answer: quantum entanglement. Schulten's theory centered on proteins called cryptochromes found in birds' eyes. When blue light hits a cryptochrome, it excites electrons in a way that creates a radical pair, two molecules each containing an unpaired electron. These two unpaired electrons become quantum entangled, their spins correlated in ways that classical physics cannot explain. Earth's magnetic field, though weak, is strong enough to influence the quantum spin states of these entangled electrons, and this influence changes the chemistry of the radical pair in detectable ways. The bird's visual system processes this quantum mechanically influenced chemistry as a sense of magnetic field direction, creating a kind of quantum compass overlaid on normal vision. The bird literally sees the magnetic field as a pattern in its visual field, enabling navigation. Experimental evidence supporting quantum entanglement in avian navigation accumulated rapidly. Researchers found that disrupting cryptochromes impairs magnetic sensing. Radio frequency fields that shouldn't affect classical chemistry, but do affect quantum spin states, interfere with bird navigation. The specific wavelength of light matters, precisely as quantum models predict, but classical models don't explain. By 2008, quantum entanglement in bird navigation had moved from speculation to serious scientific theory backed by experimental data. Once again, biology was performing quantum tricks that physics assumed were impossible in biological contexts. The warm, wet environment of a bird's eye maintains quantum entanglement long enough for the effect to influence behavior. Evolution found a way to exploit one of the universe's spookiest phenomena, entanglement across molecular distances, to solve the practical problem of navigation. If photosynthesis uses superposition and birds use entanglement, then quantum effects aren't exotic anomalies in biology. They're fundamental features that life has incorporated into essential processes. Enzyme catalysis provided another stunning example. Enzymes are protein molecules that accelerate chemical reactions, sometimes by factors of millions or billions. They're essential to life because most biochemical reactions would proceed too slowly to sustain living systems without catalytic acceleration. Classical models explain enzyme function through shape complementarity and electrostatic effects. The enzyme binds a substrate molecule, stabilizes the transition state, and lowers the activation energy barrier. But detailed studies of specific enzymes revealed something classical models couldn't explain: quantum tunneling. In certain enzymatic reactions, atoms or electrons need to cross energy barriers to reach products. Classically, particles can only cross barriers if they have sufficient energy to go over them. But in quantum mechanics, particles can tunnel through barriers, even when they lack the energy to surmount them classically. The particle's wave function extends into and through the barrier, giving it a probability of appearing on the other side. This tunneling effect becomes negligible for large objects, but significant for light particles like electrons and hydrogen atoms. Multiple enzymes exploit quantum tunneling to achieve their remarkable catalytic speeds. The particles involved literally pass through energy barriers that should block them classically, and the enzymes have evolved structures that optimize tunneling probabilities. The most dramatic example involves hydrogen transfer, a common step in enzymatic reactions. Hydrogen atoms are light enough that quantum tunneling becomes significant. Researchers studying alcohol dehydrogenase, an enzyme that processes alcohol in your liver, found that hydrogen transfer occurs much faster than classical theory predicts and shows temperature dependence, characteristic of quantum tunneling rather than classical barrier crossing. When they substituted deuterium, a heavier isotope of hydrogen, the reaction slowed dramatically, precisely as expected if tunneling was involved because heavier particles tunnel less efficiently. The enzyme had evolved to position the hydrogen at exactly the right distance and orientation to maximize tunneling probability, turning a quantum mechanical effect into a biological tool. Your body processes alcohol through quantum mechanics. The enzymes in your cells exploit tunneling routinely, and they do so at body temperature in aqueous solution, environments where quantum effects supposedly can't survive. But they do survive, and they're functional. Even more provocative is research suggesting that your sense of smell might operate through quantum mechanics. The traditional theory of olfaction, called shape theory, says that odor receptors in your nose respond to the shape of molecules. Different shapes fit different receptors like keys in locks, triggering neural signals that your brain interprets as distinct smells. This theory explains many observations but struggles with certain facts. Molecules with very similar shapes can smell completely different, while molecules with quite different shapes can smell similar. Some odors seem to depend not just on molecular shape, but on the specific isotopic composition, which shouldn't matter if only shape matters. In 1996, biophysicist Luca Turin proposed a quantum alternative, vibration theory. Turin suggested that olfactory receptors detect the vibrational frequency of molecules through a quantum process called inelastic electron tunneling. An electron tunnels across the odorant molecule, and the efficiency of tunneling depends on whether the electron's energy matches the molecule's vibrational modes. Different molecules have different vibrational spectra, creating a unique quantum mechanical signature that the receptor detects. The brain interprets patterns of receptor activation based on these vibrational frequencies as distinct smells. The evidence remains controversial, but several experiments support quantum vibration theory. Fruit flies trained to associate a particular odor with reward or punishment respond similarly to molecules with the same vibrational frequency, but different shapes. Humans can distinguish between normal and deuterated molecules, molecules identical in shape, but with different vibrational frequencies due to isotopic substitution. The ability to smell deuterated compounds shouldn't exist if olfaction depends only on shape, but it makes perfect sense if quantum vibration detection is involved. Whether or not olfaction is ultimately quantum mechanical, the fact that serious scientists consider the possibility illustrates how much the consensus has shifted. A generation ago, proposing quantum effects in the warm, wet nose would have been dismissed as pseudoscience. Now, it's a legitimate research question with experimental programs investigating it. The warm quantum paradox has dissolved. Nature maintains quantum coherence in biological systems through mechanisms we're only beginning to understand, and these quantum effects influence processes essential to life. This brings us to the most controversial and most profound question in quantum biology. Does consciousness depend on quantum mechanics? If photosynthesis, navigation, catalysis, and possibly olfaction exploit quantum effects, might the brain use them too? The idea has been explored seriously by several prominent scientists, most notably mathematical physicist Roger Penrose and anesthesiologist Stuart Hameroff, who developed a theory called orchestrated objective reduction, usually abbreviated as ORC-OR. The theory is ambitious, speculative, and deeply contested, but it addresses genuine mysteries about consciousness that conventional neuroscience struggles to explain. Understanding ORC-OR requires understanding both what it proposes and why Penrose and Hameroff felt compelled to propose something so radical in the first place. Roger Penrose is a mathematical physicist who made fundamental contributions to general relativity and was awarded the Nobel Prize in Physics in 2020. In 1989, Penrose published a book called The Emperor's New Mind, arguing that human consciousness cannot be explained by computational processes alone. His reasoning drew on Gödel's incompleteness theorems in mathematics, which prove that any consistent formal system contains true statements that cannot be proven within that system. Penrose argued that mathematicians can recognize certain statements as true, even though formal proof is impossible, suggesting that mathematical understanding transcends algorithmic computation. If consciousness were purely computational, it would be subject to Gödelian limitations, but human insight seems to transcend those limitations. Therefore, Penrose concluded, consciousness must involve non-computational physical processes. But what physical processes are non-computational? Classical physics is deterministic and computational. Quantum mechanics, specifically the collapse of the wave function, introduces an element that's both probabilistic and arguably non-computational. Penrose proposed that consciousness emerges from quantum state reduction, the moment when quantum superposition collapses into definite classical reality. But quantum mechanics as standardly formulated leaves wave function collapse as a mysterious addition to the theory. Penrose went further, suggesting that collapse is an objective physical process related to quantum gravity, the merger of quantum mechanics and general relativity. In general relativity, mass and energy curve spacetime. In quantum mechanics, particles exist in superposition of different positions, which means their mass exists in superposition of different locations, which should mean spacetime itself exists in superposition of different curvatures. Penrose proposed that when the difference in spacetime curvature between superposed states reaches a threshold related to quantum gravity, the superposition becomes unstable and collapses objectively through a process he called objective reduction. This isn't measurement by an external observer causing collapse. It's the universe itself, enforcing consistency between quantum mechanics and gravity. The threshold for objective reduction depends on the mass difference in the superposition and the time the superposition persists, with more mass difference allowing shorter superposition times. For a single electron, objective reduction would take billions of years. For large objects, like cats, it would happen essentially instantaneously, which is why we never see macroscopic superpositions. But for certain intermediate-scale quantum systems, objective reduction could happen on timescales relevant to neural processing, perhaps milliseconds, if the brain contains structures that can maintain quantum superposition for these timescales. Then, objective reduction could be the physical basis of conscious moments, each collapse corresponding to a unit of conscious experience. This is where Stuart Hameroff enters the story. Hameroff is an anesthesiologist who spent decades wondering how anesthetics eliminate consciousness. Anesthetics are chemically diverse. Some are gases, some are liquids, some are large molecules, some are small. They don't all bind to the same receptors or affect the same neurotransmitter systems, yet they all eliminate consciousness at certain concentrations. What do they have in common? Hameroff became convinced that anesthetics must act on some fundamental structure involved in consciousness itself, something common to all neurons. He focused on microtubules, protein structures that form the cytoskeleton inside cells. Microtubules are hollow tubes assembled from proteins called tubulins, arranged in geometric lattices. In neurons, microtubules maintain cell structure, transport materials, and participate in synaptic function. But Hameroff proposed they do something more. They serve as quantum computers. Each tubulin protein can exist in different conformational states, like a switch that can be on or off. If tubulins can exist in quantum superposition of these states, and if neighboring tubulins become quantum entangled through various interaction mechanisms, then a microtubule becomes a quantum computer, with thousands of qubits performing quantum information processing. Hameroff teamed with Penrose to develop the full ORC-OR theory. They propose that tubulins in neuronal microtubules enter quantum superposition, becoming entangled across many tubulins to create large-scale quantum states. These quantum superpositions are orchestrated by biological processes, hence orchestrated objective reduction. The quantum states persist for around 25 milliseconds, the timescale of conscious moments based on experimental studies of temporal perception. When the quantum superposition reaches the Penrose threshold for objective reduction, it collapses, and this collapse corresponds to a moment of consciousness. The collapse isn't random. It's influenced by the information encoded in the quantum state and by fundamental features of space-time geometry at the Planck scale, the smallest possible scale where quantum gravity effects become important. In this picture, consciousness isn't generated by classical computation among neurons. It emerges from quantum computation within neurons, specifically from orchestrated quantum state reductions in microtubules that connect to space-time geometry at the most fundamental physical level. The ORC-OR theory is controversial, to put it mildly. Many neuroscientists reject it because microtubules exist in all cells, not just neurons. Yet most cells don't seem conscious. Physicists object that the warm, wet brain should cause decoherence far too quickly for quantum states to persist 25 milliseconds. The proposed connection to quantum gravity seems speculative and unverifiable with current technology. Critics argue that classical neural computation is sufficient to explain consciousness, and that invoking quantum mechanics is unnecessary and untestable. These are serious objections, and ORC-OR remains far from accepted scientific consensus. However, several developments have made the theory more plausible than it initially seemed. First, the discovery that photosynthesis, bird navigation, and other biological systems maintain quantum coherence at warm temperatures demonstrates that biology has mechanisms to protect quantum states that physicists didn't anticipate. Perhaps neurons have similar protective mechanisms. Second, some researchers have found theoretical reasons why microtubules might maintain coherence longer than simple estimates suggest. Microtubules are highly ordered structures, and ordered systems can be more resistant to decoherence than disordered ones. The interior of microtubules is relatively isolated from the surrounding environment, providing partial shielding. Water molecules near protein surfaces form ordered layers that might reduce decoherence. Some calculations suggest that quantum coherence in microtubules could persist for milliseconds under certain conditions, though this remains debated. Third, experiments have shown that anesthetics do affect microtubules at the concentrations where they eliminate consciousness. This doesn't prove microtubules generate consciousness, but it's consistent with Hameroff's original intuition. Fourth, and most intriguingly, recent experiments have detected quantum effects in biological molecules at room temperature for longer durations than previously thought possible. In 2014, researchers led by Alexandra Olaya-Castro at University College London discovered quantum coherence persisting for picoseconds in the FMO complex involved in photosynthesis, even at physiological temperatures. While picoseconds are far shorter than the milliseconds ORC-OR requires, the experiments demonstrated that coherence can survive much longer than early theoretical predictions suggested, and the mechanisms enabling this extended coherence are still being discovered. If different protective mechanisms exist, longer coherence times might be achievable. More recently, experiments on isolated neurons have found evidence of quantum effects in ion channels, the protein pores that control electrical signaling in neurons. When ions pass through channels, quantum coherence appears to influence conductance in ways that matter for neural function. The research is preliminary, but it suggests that neurons might exploit quantum effects even if those effects don't extend to full-scale quantum computation in microtubules. Whether or not ORC-OR is correct in its specifics, the broader point stands. The brain operates at the borderline where quantum effects might persist long enough to matter. The timescales of neural processing, milliseconds to tens of milliseconds, are short enough that specially organized quantum systems could maintain coherence before decoherence sets in. The energy scales of neural signaling, involving small numbers of ions crossing membranes, are low enough that quantum effects become significant. The information processing demands of consciousness, integrating vast amounts of information into unified experiences, are complex enough that quantum computation might provide advantages over classical computation. It's at least plausible that evolution discovered ways to exploit quantum effects in neural information processing, just as it exploited quantum effects in photosynthesis and navigation. Whether consciousness requires quantum mechanics or merely uses it remains an open question, but dismissing the possibility as obviously wrong no longer reflects the scientific evidence. The experimental hunt for quantum effects in the brain continues. Researchers are developing new techniques to probe quantum coherence in living neural tissue, using increasingly sensitive measurements that can detect quantum signatures without destroying the delicate systems being studied. Nuclear magnetic resonance spectroscopy, ultrafast optical spectroscopy, and quantum sensing using nitrogen vacancy centers in diamond are all being adapted to study biological quantum effects. Some researchers are investigating whether anesthetics specifically disrupt quantum coherence rather than classical neural activity, testing predictions from ORC-OR. Others are examining whether quantum effects in ion channels could generate the precise timing and coordination observed in neural networks. Still others are searching for quantum entanglement signatures in neural activity, looking for correlations between distant neurons that exceed classical bounds. The results remain preliminary and often controversial, but the field is active and growing. One particularly intriguing line of research involves quantum effects in synaptic vesicle release. When a neural signal reaches a synapse, it triggers release of neurotransmitter molecules from tiny vesicles. The number of vesicles released is small, often just a few, and the release process appears probabilistic with significant trial-to-trial variability. Some researchers have proposed that quantum mechanics influences this probabilistic release, with quantum fluctuations determining which vesicles release in any given instance. If true, quantum randomness would directly influence neural signaling, creating a physical mechanism for quantum effects to propagate through neural networks. The hypothesis is testable by looking for characteristic quantum signatures in synaptic transmission statistics, though distinguishing quantum from classical randomness in warm biological systems is technically challenging. Another research direction examines quantum effects in the electromagnetic fields generated by neural activity. Brains generate electromagnetic fields through the collective activity of millions of neurons, and these fields can influence neural firing in turn. Some theories propose that consciousness emerges from quantum effects in these electromagnetic fields rather than from quantum effects within individual neurons. The idea, developed by researchers like John Joe McFadden, is that the brain's electromagnetic field serves as a quantum mechanical workspace, where information from across the brain becomes integrated through quantum superposition and entanglement. Measurements suggesting that consciousness correlates better with electromagnetic field properties than with individual neural firing patterns lend some support to this electromagnetic field theory of consciousness, though alternative classical explanations exist. Regardless of which specific mechanism proves correct, if any, the accumulating evidence points toward a conclusion that would have seemed absurd to 20th century neuroscientists. The brain likely exploits quantum mechanical effects in its normal functioning, whether these quantum effects are essential to consciousness or merely useful for certain computations, whether they occur in microtubules or membranes or electromagnetic fields, whether they persist for milliseconds or mere microseconds. The warm quantum paradox has been resolved. Biology can maintain quantum coherence at body temperature through various protective mechanisms. Evolution has had billions of years to discover and refine these mechanisms. The brain, the most complex information processing system known to exist, operates at precisely the regime where quantum effects transition from dominant to negligible. It would be surprising if evolution hadn't exploited quantum mechanics somewhere in neural function. Understanding that your brain might function partly through quantum mechanics transforms how you think about consciousness. The quantum superposition of concepts we explored earlier might not be just mathematical analogy. It might reflect genuine physical superposition of neural states, quantum coherence maintained long enough to influence thought. The measurement problem in consciousness, the question of how definite experiences emerge from probability clouds, might be the same measurement problem that physicists grapple with in quantum mechanics. When you make a decision and feel possibility collapse into actuality, you might be experiencing objective reduction, the universe enforcing consistency between quantum mechanics and space-time geometry through a process that generates your conscious experience. Your sense of free will, the feeling that you genuinely choose among alternatives, might reflect quantum indeterminacy in neural processes. Choices wouldn't be predetermined by prior physical states if quantum randomness influences neural dynamics. The future would be genuinely open, with your decisions participating in collapsing quantum possibilities into classical actuality. But quantum mechanics in the brain also raises profound questions about the nature of consciousness itself. If conscious experience correlates with quantum state reduction, what exactly is doing the experiencing? Quantum mechanics describes physical processes mathematically, but experience, qualia, the feeling of what it's like, seems to be something beyond physics. This is the hard problem of consciousness that philosopher David Chalmers identified, the question of why there is subjective experience at all. Quantum mechanics doesn't solve the hard problem automatically. You could have quantum computation in microtubules without any accompanying experience. But quantum mechanics does change the playing field by introducing fundamental indeterminacy and measurement-dependent reality into the physical description of the brain. Classical physics describes a deterministic mechanical brain, where consciousness seems like an awkward addition. Quantum physics describes an indeterministic observer-dependent brain, where consciousness might play a constitutive role. The quantum brain is a brain that requires observers, measurers, collapses of possibility into actuality. And what is consciousness if not precisely that? The process by which possibility becomes experience. The warm, quantum coherence in your brain, if it exists, operates within the fractal architecture we explored previously. The two principles aren't separate. Fractal organization might enable quantum coherence by creating structures at just the right scales to maintain quantum effects before decoherence sets in. The hierarchical, self-similar organization of dendrites and neural networks creates protected pockets where quantum states could persist. The critical dynamics that generate fractal temporal patterns might also create conditions favorable for quantum coherence, as criticality typically does. Your brain might be simultaneously fractal and quantum, with each property enabling and enhancing the other. The fractal structure provides the scaffold. The quantum mechanics provides the subtle dynamics. Together, they generate the extraordinary phenomenon of consciousness, your moment-to-moment experience of being aware, making choices, and participating in reality's unfolding. We've journeyed from the impossibility of warm quantum effects to the accumulating evidence that life found ways to achieve the impossible. Photosynthesis harnesses superposition. Birds navigate using entanglement. Enzymes exploit tunneling. And your brain, the most sophisticated information processor in the known universe, likely uses quantum mechanics for reasons we're only beginning to understand. The quantum nature of consciousness isn't established fact. It remains hypothesis, speculation, frontier science with more questions than answers. But the questions have transformed from whether quantum effects could possibly matter in biology to how they matter, where they matter, and what they contribute to the miracle of awareness. The warm quantum paradox dissolved, and in its place emerged a new picture of life operating at the edge of the quantum classical boundary, exploiting the best of both worlds. But if consciousness leverages quantum mechanics within fractal neural architecture, where does consciousness exist? Is it produced by the physical brain, or does the quantum nature of thought suggest something more radical? To answer this, we need to explore a vision of reality proposed by physicist David Bohm, one that suggests the universe itself is holographic, with consciousness accessing dimensions of order deeper than the physical world we perceive. The quantum and fractal patterns we've discovered might be surface manifestations of something far more profound. Chapter 5. The Holographic Mind and Implicate Order. In 1959, physicist David Bohm was contemplating the paradoxes of quantum mechanics when he had a revelation that would reshape how we understand reality itself. Bohm had been Einstein's protege, and like Einstein, he felt dissatisfied with the standard interpretation of quantum mechanics. The Copenhagen interpretation, the mainstream view, suggested that particles don't have definite properties until measured, that reality is fundamentally probabilistic and observer-dependent. Einstein famously objected that God doesn't play dice, and Bohm shared this discomfort with radical indeterminacy. But instead of rejecting quantum mechanics, Bohm proposed something far more radical. What if the quantum world we observe is just the surface of a much deeper reality? What if beneath the probabilistic, particle-like behavior we measure lies an implicate order, a dimension of existence where everything is enfolded into everything else, and the separate, definite objects we perceive are merely ripples, temporary unfoldings from this deeper wholeness? Bohm called the world of appearances the explicate order, explicate meaning unfolded, the realm of distinct objects existing in space and time. But he proposed that this explicate order emerges from an implicate order, implicate meaning enfolded, a dimension where everything interpenetrates everything else, where separation is illusion and wholeness is the fundamental reality. To understand Bohm's vision, consider a hologram. In ordinary photography, each point on the film records light from one specific point on the photographed object. Damage part of the photograph, and you lose information about part of the object. But holographic film works differently. Light from every point on the object reaches every point on the holographic film, with the pattern encoded as an interference pattern, created by splitting laser light and recombining it. The remarkable property of holograms is that if you cut a holographic film in half, you don't get half the image. Each half contains the entire image, just with lower resolution. Cut it into quarters, and each quarter still contains the whole image. Every part of the hologram contains information about the whole. The part contains the whole, enfolded within it. Bohm realized that quantum mechanics suggests the universe operates holographically. The wave function of a particle isn't localized at the particle's position. It extends throughout space, carrying information about the entire quantum system. Every region of space contains information about every other region through quantum entanglement. The universe is more like a hologram than like a classical arrangement of separate objects. Everything is enfolded into everything else at the quantum level, and what we experience as separate, localized objects are explicate forms that have temporarily unfolded from the implicate order. The implicate order isn't a place or a substance. It's a different kind of order, a different way that things can be organized. In the explicate order, objects are distinguished by their position in space and time. The chair is here, the table is there, they're separate objects with definite locations. But in the implicate order, the chair and table aren't fundamentally separate. They're aspects of a unified field that enfolds all possibilities, and their apparent separation is a temporary unfolding, like waves rising from an ocean. The waves seem separate, with distinct peaks and troughs, but they're all expressions of the same water, the same underlying medium. Bohm suggested that space and time themselves are features of the explicate order, the unfolded dimension, while the implicate order is a temporal and a spatial, a dimension of pure relation and potential. Everything that exists in space and time is a projection from this deeper dimension, and the deeper dimension contains everything simultaneously, not as separate entities, but as interpenetrating aspects of an undivided wholeness. This might sound like mystical speculation, but Bohm grounded it in serious physics. His alternative interpretation of quantum mechanics, called the de Broglie-Bohm theory or pilot wave theory, reproduces all the predictions of standard quantum mechanics while providing a deterministic underlying reality. In Bohm's interpretation, particles always have definite positions, but they're guided by a quantum potential that depends on the wave function of the entire system. The quantum potential connects everything to everything else instantaneously, regardless of distance, providing a physical mechanism for the non-locality that quantum entanglement demonstrates. The quantum potential is the implicate order acting on the explicate order, guiding particles according to the information enfolded in the universal wave function. When you measure a particle, you're not creating its properties through observation. You're interacting with its position as guided by the quantum potential that connects it to everything else in the universe. The measurement reveals something that was always there, but was determined by relationships extending through the entire implicate order, rather than by local separable properties of the particle itself. Bohm's vision of implicate and explicate orders provides a framework for understanding the holographic nature of reality that quantum mechanics reveals. Quantum entanglement demonstrates that measuring one particle affects another instantaneously regardless of distance, suggesting they're not truly separate entities. They're different aspects of a single quantum system, and that system exists fundamentally in the implicate order where separation is merely apparent. When particles become entangled, they're revealing their inherent unity in the implicate dimension. The correlation between them doesn't require communication across space, because in the implicate order, they were never actually separated. Space itself is a feature of explicate unfolding, not a fundamental aspect of reality. The deeper reality is holographic, with every part containing information about the whole, and quantum entanglement is simply the manifestation of this holographic structure in the explicate domain we inhabit. This holographic principle has found surprising support from theoretical physics developments that occurred decades after Bohm proposed his philosophy. In 1993, physicist Gerard 't Hooft and later Leonard Susskind developed the holographic principle in the context of black hole thermodynamics and string theory. They demonstrated that all the information contained in a volume of space can be encoded on the boundary of that volume, like a hologram encoding three-dimensional information on a two-dimensional surface. A black hole's information capacity depends on the area of its event horizon, not its volume, suggesting that our three-dimensional universe might be a holographic projection from information encoded on a distant, two-dimensional surface. The ADS-CFT correspondence, one of the most important discoveries in theoretical physics, mathematically proves this holographic relationship for certain special spacetimes. Our universe might literally be a hologram, with the three-dimensional space we experience emerging from deeper dimensional structures that encode reality in holographic form. Bohm intuited this holographic nature of reality from quantum mechanics. Modern physics is confirming it through multiple independent routes. The implications for consciousness are staggering. If reality is fundamentally holographic, with every part containing the whole, then your brain might not be a localized processor that generates consciousness. Your brain might be a holographic fragment of a universal consciousness, containing information about the whole within its particular structure, accessing and manifesting a localized perspective on something fundamentally non-local and unified. Consciousness wouldn't be produced by neurons. It would be revealed through neurons, unfolded from the implicate order into explicate experience. This is precisely what neuroscientist Carl Pribram proposed when he developed the holographic brain theory, independently of Bohm's work, though later the two collaborated to integrate their ideas. Pribram's journey to holographic brain theory began with experimental puzzles about memory. In the 1920s, neuroscientist Carl Lashley spent decades trying to locate where memories are stored in rat brains. He trained rats to run mazes, then systematically removed different parts of their cortex, expecting to find the memory storage location. But no matter which part he removed, the rats retained memory of the maze, though with degraded performance proportional to the amount of tissue removed. The memory didn't seem to be stored in any particular location. It was distributed across the entire cortex, and removing part of the brain degraded the memory without erasing it entirely. This was exactly like cutting a hologram in half. You get the whole image with lower resolution, not half the image with full resolution. Pribram, working in the 1960s and 70s, realized that if memories are stored holographically, the puzzling experimental results make perfect sense. Every part of the cortex contains information about all memories, encoded as interference patterns distributed across neural networks. Damage to part of the cortex reduces the clarity of all memories rather than eliminating specific memories completely. But how could neural tissue store information holographically? Pribram focused on the mathematical similarities between holographic storage and neural processing. Holograms encode information through interference patterns created by wave interactions. The brain processes information through electrical and chemical waves propagating through neural networks. Specifically, Pribram noted that neurons communicate not just through action potentials, the digital spikes typically emphasized in neuroscience, but through graded potentials, continuous wave-like changes in electrical potential. These graded potentials create interference patterns across dendritic fields, and these interference patterns could encode information holographically. Moreover, the brain performs Fourier analysis, a mathematical technique fundamental to holography. The visual cortex doesn't represent images as arrays of pixels. It decomposes visual information into spatial frequency components, essentially performing a Fourier transform that converts spatial patterns into frequency spectra. This is exactly the mathematical operation involved in creating and reading holograms. The brain naturally operates in the frequency domain that holography requires. Pribram proposed that memories are stored as interference patterns in the frequency domain across vast neural networks. When you recall a memory, the brain performs something like the optical reconstruction of a hologram, transforming frequency domain information back into spatial domain experience. This explains several mysterious properties of memory. Memories are content addressable, meaning you can recall an entire memory from a partial cue, just as you can reconstruct a complete holographic image from a fragment of holographic film. Memories gracefully degrade rather than catastrophically failing, because holographic storage is robust to partial damage. Memories can be triggered by unexpected associations, because the holographic storage naturally creates connections between patterns that share frequency components. The capacity of memory seems nearly unlimited, as holographic storage can encode massive amounts of information through overlapping interference patterns in the same neural substrate. All of these properties follow naturally from holographic organization but are difficult to explain with conventional localist models of memory storage. The holographic brain theory also explains a curious phenomenon called blind sight. Patients with damage to primary visual cortex report being blind in parts of their visual field, claiming they see nothing. But if you ask them to guess what's in the blind region, they guess correctly far above chance level. They have visual information they're not consciously aware of possessing. In holographic terms, the damaged cortex no longer provides enough resolution to consciously reconstruct detailed visual experience, but enough holographic information remains distributed across other areas to enable unconscious visual processing. The patient is like someone looking at a badly degraded hologram that no longer shows clear images, but still contains enough information to influence behavior. Consciousness might require a threshold of holographic resolution to generate vivid, explicate experience, but below that threshold, implicate order information can still influence brain function unconsciously. Pribram and Bohm eventually joined forces to develop a comprehensive vision of reality, where the brain is a hologram perceiving a holographic universe. In this framework, the brain doesn't create a representation of an external objective world. The brain participates in unfolding the implicate order into explicate experience, and both brain and world are different aspects of the same underlying holographic reality. When you perceive a tree, you're not creating an internal model of an external tree. You're unfolding the aspect of the implicate order that manifests as tree experience, and the neural activity in your brain is part of that unfolding, not separate from it. The subject-object distinction dissolves because both subject and object are explicate manifestations of the same implicate whole. Your consciousness and the tree's existence are complementary unfoldings, like two waves from the same ocean, appearing separate in explicate space and time, but unified in the implicate dimension from which they both arise. This holographic vision explains phenomena that seem impossible in conventional materialist frameworks. Intuition, the ability to know something without conscious reasoning, makes sense if your brain holographically accesses information from the implicate order where everything interpenetrates everything else. You're not mysteriously receiving information across space and time. You're accessing information that's already enfolded within the holographic structure of your neural networks, information about the whole that's present in every part. Creativity, the generation of genuinely novel ideas, becomes explicable as unfolding new patterns from the infinite potential of the implicate order. You're not creating from nothing. You're allowing new forms to unfold from the timeless dimension of pure potential that underlies all manifestation. Synchronicity, meaningful coincidences that seem too perfectly timed to be random, can be understood as multiple explicate events unfolding from the same implicate pattern. They're not causally connected through time, but correlated through their shared origin in the deeper order. The holographic model also provides a framework for understanding consciousness beyond the individual brain. If every part contains the whole in holographic reality, then every individual consciousness contains information about universal consciousness. You're not a separate fragment of awareness isolated in a skull. You're a localized unfolding of awareness that remains connected to the whole through the implicate order. Your personal consciousness is like a wave that has temporarily risen from an ocean of consciousness, appearing individual from the surface perspective, but remaining the ocean in essence. Other people's consciousnesses are other waves from the same ocean, seemingly separate in explicate space but unified in the implicate depth. This explains why deep meditation or mystical experiences often involve a sense of losing individual boundaries and merging with universal consciousness. You're not experiencing something imaginary. You're shifting attention from the explicate level where separation appears real to the implicate level where unity is fundamental. The separateness was always a kind of illusion, a limited perspective from within the explicate unfolding. But the most profound implication of holographic reality concerns the relationship between consciousness and the physical world. In the conventional materialist view, consciousness is produced by physical brains, an emergent property of sufficiently complex information processing. But if reality is fundamentally holographic, the causal arrow might run the opposite direction. The physical world might be what consciousness looks like when viewed from within the explicate order, while consciousness itself exists primarily in the implicate dimension. Your brain wouldn't generate consciousness. Your brain would be the explicate form that consciousness takes when it localizes itself in space and time. The hard problem of consciousness, why physical processes generate subjective experience, dissolves because physical and experiential are not different kinds of things. They're different orders of the same reality. Physical is the explicate order, viewed objectively. Experience is the implicate order known directly. They're two perspectives on one holographic reality, and you exist in both simultaneously. This perspective resonates with quantum mechanics in revealing ways. The measurement problem, why quantum superpositions collapse into definite states when observed, becomes less mysterious if observation is the process by which consciousness unfolds possibilities from the implicate order into explicate actuality. The quantum wave function exists in the implicate order as pure potential, enfolding all possibilities. Consciousness, through observation, unfolds specific, explicate realities from that potential. The collapse isn't a physical process in the usual sense. It's a transition between orders of reality, from implicate to explicate, and consciousness is the agent of that transition, because consciousness bridges the two orders. You exist simultaneously in both dimensions, the implicate source of your awareness and the explicate form of your embodied experience. When you observe a quantum system, you're not just recording pre-existing information. You're participating in unfolding implicate potential into explicate actuality, and the specific actuality that manifests depends on the context of observation, because context determines how the unfolding occurs. The holographic principle also sheds light on the phenomenon of quantum entanglement that seems to violate locality. When two particles are entangled, measuring one instantaneously affects the other, regardless of the distance between them. Einstein found this deeply troubling, calling it spooky action at a distance, because it seemed to require faster-than-light communication. But in holographic reality, there's no mystery. The entangled particles aren't truly separate entities located in distant regions of space. They're different explicate manifestations of a single holographic pattern in the implicate order. Measuring one particle unfolds information that's already present throughout the holographic structure, simultaneously determining the state of both particles, because they're aspects of one underlying reality. No information travels through space, because the correlation exists in the implicate dimension that transcends space. Entanglement is simply what non-locality looks like when you're viewing it from within the explicate order where space seems real and fundamental. This holographic understanding of entanglement extends to consciousness in illuminating ways. When you develop a deep relationship with another person, you might say you're entangled with them psychologically. You think of them and they call. You sense their emotional state without being told. Your mental states become correlated in ways that seem mysterious. In holographic terms, your consciousnesses have become entangled in the implicate order, creating correlations that manifest in the explicit order as coincidental timing, emotional resonance, and intuitive knowing. The correlation isn't caused by sensory information transfer. It exists at the deeper level, where your consciousness and theirs are different unfoldings from the same holographic source. The closer the relationship, the more the implicate patterns overlap, creating stronger correlations in explicate experience. This isn't mystical nonsense. It's what holographic consciousness predicts should happen when two localized unfoldings interact intensely enough to create shared patterns in the implicate order. The concept of collective consciousness makes perfect sense in holographic framework. Cultures, communities, and even humanity as a whole can share implicate patterns that manifest as collective beliefs, emotional atmospheres, and coordinated behaviors that seem to transcend individual communication. When a society undergoes rapid change, when social movements suddenly emerge simultaneously in multiple locations, when zeitgeist shifts palpably even for those not directly connected, you're witnessing explicate manifestations of changes in the implicate order that contains all individual consciousnesses as holographic fragments. The collective isn't just the sum of individuals. It's a holographic pattern at a larger scale, containing information about all members while being more than their simple aggregation. You participate in multiple levels of holographic consciousness simultaneously: individual, familial, cultural, species, and ultimately universal. This multi-level holographic structure connects to the fractal architecture we explored earlier. Fractals are self-similar across scales, with each level containing patterns that mirror other levels. Holograms are similar, with each part containing the whole at different resolutions. Fractal and holographic organizations are mathematically related, both expressing the principle that information about the whole is distributed throughout the structure, rather than localized in discrete components. Your consciousness is simultaneously fractal and holographic, exhibiting self-similar patterns across temporal scales, while containing information about the universal consciousness from which it unfolds. The fractal dimension provides the temporal and structural organization. The holographic principle provides the informational content and connectivity. Together, they create a consciousness that spans scales from milliseconds to lifetime, from neural activity to cosmic awareness, maintaining coherence across all levels through the implicate order that enfolds everything into everything else. Accessing the implicate order directly becomes the goal of certain contemplative and spiritual practices when understood through Boehm's framework. Meditation techniques that quiet discursive thought and sensory processing aren't just relaxation methods. They're technologies for shifting attention from the explicate order, where you seem to be a separate self in a world of separate objects, to the implicate order, where you recognize yourself as an unfolding of undivided wholeness. The sense of unity, the dissolution of subject-object boundaries, the experience of timelessness that characterize deep meditative states aren't hallucinations or wishful thinking. They're direct perception of the implicate dimension that's always present, but usually obscured by absorption in explicate unfolding. You're not achieving a special state. You're recognizing the actual nature of reality that was always there beneath the appearance of separation. Boehm himself was deeply influenced by dialogue with the Indian philosopher Jiddu Krishnamurti, and together they explored how thought creates the illusion of separation. In Boehm's analysis, thought operates by creating divisions, distinguishing this from that, self from world, observer from observed. These divisions are useful for practical functioning in the explicate order, but they're not ultimately real. They're conventions that become problems when mistaken for fundamental reality. The separate self that you take yourself to be is a thought-created structure, an explicate form that has forgotten its origin in implicate wholeness. Suffering arises from this forgetting, from the sense of being an isolated fragment in a fragmented world. But meditation, inquiry, and direct perception can reveal the implicate order, not as something different from ordinary experience, but as the depth dimension of ordinary experience. The tree you see isn't just a separate object out there. It's an unfolding from the same source as you're seeing, and recognizing this doesn't require belief or imagination. It requires only clear perception of what's actually happening beneath the conceptual overlay. The holographic brain, accessing holographic reality, explains seemingly paranormal phenomena in naturalistic terms. Remote viewing, the claimed ability to perceive distant locations without sensory access, makes sense if consciousness holographically contains information about the whole. You're not mysteriously projecting awareness across space. You're accessing information already present in the implicate order, where distance doesn't apply. Precognition, knowing future events before they occur, becomes less paradoxical if the implicate order is atemporal, containing past, present, and future as different explicate unfoldings from the same source. You're not literally seeing the future. You're accessing implicate patterns that will unfold into specific explicate futures, though the unfolding remains partly open because consciousness participates in determining how potential becomes actual. Telepathy, mind-to-mind communication, is what you'd expect when two consciousnesses are holographically connected in the implicate order. You're not transmitting thoughts through space. You're recognizing that in the implicate dimension, your mind and another mind are different aspects of one awareness that naturally shares information. These phenomena remain controversial scientifically, and the evidence for them varies from suggestive to weak, depending on the specific claim. But the holographic model at least provides a theoretical framework where such phenomena aren't impossible violations of known physics. They're what you'd expect if consciousness operates holographically, accessing and unfolding information from the implicate order. Whether the effects are real and strong enough to be reliably detected remains an empirical question. The point is that holographic consciousness predicts certain possibilities that materialist consciousness considers impossible in principle, and that's a testable difference. As experimental methods improve and theoretical understanding deepens, we may discover that consciousness has capacities that conventional neuroscience never imagined, because it never considered that the brain might be a holographic interface to implicate dimensions of reality. The holographic mind also transforms how you understand learning and knowledge. When you learn something new, you're not just adding information to a database in your brain. You're reorganizing the holographic interference patterns across your neural networks, changing how the implicate order unfolds through your consciousness. Deep understanding isn't accumulation of facts. It's recognition of patterns that were always present in the implicate order, but inaccessible until your neural hologram develops the right structure to unfold them. This is why insight often feels like remembering rather than discovering. Why truth rings true, even when you encounter it for the first time. You're not learning something completely foreign. You're recognizing something that was always enfolded in the holographic structure of reality, now becoming explicit through your particular unfolding. All knowledge exists in the implicate order as potential, and education is the process of developing neural structures sophisticated enough to make that potential explicit through holographic reconstruction. This has practical implications for how you approach learning and problem-solving. Instead of trying to force understanding through purely analytical thinking, you can learn to quiet analytical mind enough to allow holographic insight to emerge. The answer to a problem might already be present in your neural hologram, inaccessible to conscious analysis, but available to intuitive perception if you create space for it. Many great discoveries involve periods of intense conscious work, followed by letting go, and the solution appears spontaneously, often during relaxation or sleep. The conscious work reorganizes the neural hologram, and the letting go allows the holographic reconstruction to complete without interference from analytical thought trying to force specific outcomes. You're not giving up. You're shifting from explicate manipulation to implicate unfolding, letting the deeper order reveal solutions that conscious effort alone couldn't reach. The holographic model of mind and reality represents one of the most profound shifts in scientific worldview since quantum mechanics itself. Where classical science saw a universe of separate objects interacting through local forces, holographic science sees a unified field where everything interpenetrates everything else, with apparent separation being a surface feature of explicate, unfolding from implicate wholeness. Where neuroscience saw brains generating consciousness through computational complexity, holographic theory sees brains as interfaces through which consciousness manifests locally while remaining fundamentally non-local and unified. Your brain doesn't produce your awareness. It focuses and localizes awareness that exists in the implicate order, giving it specific explicate form. You're simultaneously the localized unfolding and the universal source, the wave and the ocean, the holographic fragment and the whole it contains. We've journeyed from Bohm's philosophical intuitions about implicate order, through Pribram's neuroscientific evidence for holographic memory, from quantum mechanics revealing non-locality, to modern physics confirming holographic principles mathematically. The vision is coherent, explanatory, and increasingly supported by diverse lines of evidence. But it's also unsettling because it challenges every assumption about being a separate self in an external world. If you take the holographic model seriously, your relationship to reality transforms completely. You're not in the universe. The universe is in you, holographically enfolded in your consciousness. Your thoughts and perceptions aren't private, internal representations. They're local unfoldings of patterns that exist in the implicate order accessible to all consciousness. The boundary between your mind and the world dissolves because they're both explicate manifestations of implicate wholeness. But this raises an immediate practical question. If you truly are a holographic fragment of universal consciousness, if you have access through the implicate order to information and capacities beyond your individual brain, how do you actually use this? How do you deliberately harness quantum cognition, fractal awareness, and holographic consciousness in everyday life? The answer involves learning to think in ways that honor your mind's actual architecture, rather than fighting against it. You need to learn quantum thinking. Still here, friend? If your eyes are getting heavy, it's okay to let them close. Your mind remembers the way. But if you're still awake, there's another video waiting for you. I'll be here if you'd like a little more company. Either way, thank you for spending your night here. May your dreams be calm, your breath gentle, and your thoughts float softly like stardust. Sleep well among the stars.